So my first question is on the paper, you make a comment, and I think you've said this a few times, including when we chatted there in French, that many of the past solutions overfit. And could you be specific about what you mean by overfitting? Do you mean the validation loss is higher than the training loss, or what do you mean specifically?
Of course, the competition metric. I don't care about the loss. We're in a competition, there is a metric, a score.
Yeah.
So when you do Kaggle, so the purpose of machine learning is to build models that work well on unseen data. It's generalization, right? And because most LLM benchmarks and previously machine learning benchmarks have a public case data, people believe that the goal of machine learning is to build a model that does well on the test data. And they use the test data to select the model, to select the checkpoint, to select the prompt, whatever you're doing. And as a result, they build models that do well on the test data, but not so well on new data. That's what I mean by overfitting. So in Kaggle, overfitting is when it's seen by the difference in score between the public leaderboard and the private leaderboard. So for those who don't know, on Kaggle, during competition, you submit your solution, which is code that Kaggle will run on a hidden test set. But Kaggle will give you a score on, so far prize it was half of the test puzzles. And that's called the public leaderboard. So during competition, you see a score. And that's an half of the test data. You don't see the test data, but the final ranking of the competition is the score on the other half of the test data. And you don't have feedback from it till the end of the competition.
Right.
And they design it this way to make sure that they measure the generalization ability of your solution, because you have no information from the hidden test. So at the end of the competition, you must select what you believe is your best solution, and then the hidden test set score for that selected solution is your final score. So it means you have to select your model before you know the test score. And this changes everything compared to every other benchmark. Because in every other benchmark, you can select the model based on the score test. So everybody overfits to test data. It's a disease. But on Kaggle, you cannot overfit because you don't have access to it. But my experience is, I'm known on Kaggle to not overfit. I'm one of the best at this. And in every competition, we see people with a high score on the public and they drop on the private because they overfit. They just use the feedback from the public leaderboard to guide what they do. And in our case, we didn't use the public leaderboard feedback at all. We just use our local setting, which is based on the public evaluation data set from our prize.
Right.
So, and it shows we dropped by less than 15% from public to private, and other top teams, they lost 1/3 of their score or even more between public and private.
Right.
So it's, and I was not surprised. I have observed this. Only experienced Kagglers are good at not overfitting at all.
Right.
So that's what I mean. The drop from public to private leaderboard means overfitting.
Right. That's clear. If I had one sentence to summarize your success this year, or the level of success you achieved with Ivan, I would say, and I want you to agree or disagree with this, I would say the secret that you found is to combine existing tasks to create new, more difficult tasks, and therefore have a broader coverage in your training data.
Yeah, it's just synthetic data, which is our secret weapon. And it's not so much the number of new puzzles, because there are data sets with more puzzle like ARC. It's a quality, indeed. And it's mostly Ivan work. So I spent time, I spent like 4 months building a good data generator pipeline using frontier models. But basically, you could say, so what you say is right. Another angle is, which amounts to the same. To do well on ARC prize, you must understand the transition from input to output. So the transformation, you need to infer a transformation from few examples only. And to do it correctly, you need to generate Python, basically. So if you look at top solution and the ARC AGI leaderboard, they generate Python code on the fly using frontier models. But we could not do it on Kaggle because of the compute limit. We only have 4 small GPUs and 4 for only 12 hours for all the tasks. So it's a budget of 20 cents per task. And you cannot use frontier model because you don't have internet. So given all of this, we looked at ways of moving the puzzle understanding and code generation offline. And that's the basis of the reason why we generated data, because we use frontier model to do reasoning and code generation, and then distill the result into a smaller model. And we use the smaller model in Kaggle.
Right. So I want to talk about 3 parts of the paper. There's the data preparation, there's the architecture, and then there's the TRM portion. And I'll spend most of my time on the data preparation. I know Ivan has done a lot of that. But even within data preparation, I can see 2 big pieces. The first piece is the seed data set. You need to have a seed data set. And then the second piece is the data set expansion. So that's the generation of the synthetic data. And I want to start off with the seed data. Maybe you could talk a bit about where the seed data comes from. And yeah, let's start with that.
It's a bit more complex because you have seed data, but so what you want, if you want to fine tune, if you want to use LLMs to generate new data, you need to have, you just giving them few samples, they need help. So you need a description of the puzzle. And there is a data set called ARC, Human ARC.
Human ARC, yeah.
Where the people who built that recorded human explanation. So they gave ARC AGI I problems to people, and they asked them to write down what they were doing to solve the problem, basically. So you had a text describing how to solve those problems. So you have like 1,700 descriptions. So many tasks have several descriptions. So that's a good context for LLMs. But then Ivan structured it more. So he first used LLM, Claude, at the time, to describe. So using these human stories, let's say, to create a description of puzzle in a structured way. So a puzzle, he called these summaries. So you have a description on how to create input grids. So, like for instance, input grids, you have several anchor points of different colors. Solution step, what is a transformation? So then it would be draw a green line, a horizontal green line when you have 2 anchors of the same color in a given line. And then draw red lines vertically when you have 2 points of the same color in a column. Then a summary of the rules. So like drawing lines between points of the same color in a line, in a row or a column. Key insights, main ideas. So it's drawing lines here. I took a very simple example, so it looks like a bit redundant, but for more complex,
Sure.
each rubric has its meaning. And then the puzzle concept, or line drawing. So he built from each arc a series, a description of ARC AGI I. He also looked, there is a data set called BARC, which is created from human prompts. So he took these, filtered, the one that did not fit his way. So basically, in BARC, there are some mistakes. So some tasks don't have a concept, or there are a few things he filters. But he collected like 600 tasks from BARC, and same used LLM to generate his 5 rubrics. So at the end, he had a number of, he had like 700 puzzle. And for each puzzle, he generated 3 summaries, 2 using Claude and 1 with GPT-OSS. So he had like 2K puzzle summaries. And then, so that's the seed. So the seed it's not the raw data set, it's the description in his format of puzzle in the data set.
Right.
So that's what he calls a seed. So it's already pretty heavily processed.
Yeah.
And then he used LLMs to generate new descriptions by combining the puzzle descriptions.
Right.
And for this, he used GPT-OSS and generated 260K new puzzle summaries, basically. So he had a huge 260K puzzle descriptions.
Yeah.
These are just textual, not actual puzzles.
Right.
I can continue if you want.
Let me maybe paraphrase some of what you've said, because I think there is some detail that leads to a lot of the performance you got. The first step is there is HARC and there is BARC. Those provide a description of tasks for ARC AGI I, which are easier than ARC AGI II. And a core improvement you're just explaining is that rather than rely just on a simple description, there is instead, it's like a JSON file with key value pairs for a more broken down form of that description, namely describing the input grid, describing some of the concepts. And that's generated through augmentation using an LLM. So that gives you a better description than the raw human ARC descriptions or BARC provide, right?
Yeah, it's more structured. And you're right. These were ARC AGI I. And so when Ivan generated puzzles from these and pre-trained models, he could not get more than few percents on the ARC prize leaderboard. So he thought it's because ARC AGI I tasks are too simple. So he looked at ARC AGI II task.
Right.
And generating this LLM descriptions from the puzzle was tricky. So he did it by hand for 29 of them, but doing one takes like half an hour. So it's
half an hour, yeah.
So after having done 29, he had a better idea of how to prompt LLM to do it. So he prompted Claude to label the remaining evaluation task and the training. The training tasks are easier. But the quality of the Claude descriptions is not as good. He kept them, but it's not the same quality. So there is potential for improvement to do hand descriptions of the remaining ones.
Right. Yeah. So to give the viewers a sense of numbers, there are 800 ARC AGI I tasks, 400 training, 400 evaluation, and human ARC, HARC, and BARC roughly cover that data set. So you have descriptions available that you can then augment and expand like we described. But then, as you mentioned, Jean-Francois, the problem is those problems are, the tasks are too easy. So you need ARC AGI II difficulty, but those don't have human descriptions available online. And so you were forced to write them by hand. Plus then, because it was such a pain, you wrote some with Claude 4.5, which probably can get some decent ones, but it's not going to get them all right.
There is also an overlap, especially the training task of ARC AGI I overlap a lot with ARC AGI II. The training task of ARC AGI II overlapped with ARC AGI I. So it's mostly the evaluation part of ARC AGI II, which is the hardest, and the ones not covered in ARC AGI I. So these are the one that I've hand labeled for part and then use Claude. And then, so he had all these puzzles description, applying so using GPT-OSS 120B to mix. So from two puzzle descriptions, create a new one. For the listeners, all the prompts we used for data generation are in our GitHub repo. So what I'm describing, it's straightforward when you see the prompts. You just see the logic that was used. So then we have puzzle descriptions and combinations. As I said, 260K.
Yeah.
And now we have to create actual puzzles.
Yeah.
So that's where code generation comes in. So other people generated puzzle from text like BARC or real but so the novelty here, all the previous work, they generate the full puzzle. So a puzzle in ARC AGI, set of pairs, input, output. So little grids with colored pixels, and you have a rule per puzzle that maps the input to output. So you have to create a set of pairs, input, output for the puzzle. Then you can decide some of these are tests, some are trained, but that's a detail. You need to create pairs of puzzles that are consistent. So the input should look similar in a way. The output should look similar in a way, and the transformation between input and output should be the same across all pairs. And Ivan decided to break the process in two. So first, generate inputs,
right,
that come from the same distribution, let's say, that are same family, and then generate outputs from each of the input. So so he has a textual description, then he has LLM, GPT-OSS. So people ask why GPT-OSS and not Claude. It's because we have a limited bandwidth, number of tokens we can use, even at NVIDIA.
Right.
And doing at scale, the data generation was just too long. So using a source of good quality, maybe it's not as good as Claude, but it was good enough. So he first generated what he calls input logic.
Yep.
So code to create input grids.
Yep.
And he also generate, so he has the prompt as the LLM given a puzzle description, generate code to generate grids, and also generate unit test. So constraint that the grid must have. And then, so from this, you can generate a puzzle, and the requirement is to generate to be able to generate 30 grids. So each puzzle must have at least 30 grids. So if it cannot, so generating means running the generating code and then running all the unit test.
Yeah.
The one that's the And then there is the output generation. So here,
Right.
again, asking the LLM to generate code to create output grids. And instead of generating code once and unit tests, he said, let's generate. So you still have the same textual description. So you know in text what the transformation is. He asked the LLM to generate 20 times the transformation code, and he ran it.
Yeah.
And keeps the most common. So it's hard to explain. So you have 20 transformation code. So he runs the 20 transformation code on the inputs.
Yeah.
And then he looks at which one I put the same. So if two transformation code compute the same output across, then
across all 30 inputs.
Yes.
Yeah.
And then he keeps the most frequent group.
Yeah.
So let's say out of the 20, you have 12 procedure that produce same output across. So that then you keep those out you've captured.
Right.
But if all the code have different values, so the most frequent is only 7, it drops.
Yeah.
It says I need at least 8 out of 20 to agree. So
I see.
A tune, but so the goal is not to keep the generating code, it's to keep the output grids. Basically, so if the LLM has 20 times, produces 10 times the same output grids, then that's good. The output grids are kept.
So do you end up with about 30 example pairs per task?
Yes.
And do you use all of those in both TRM and architects or no?
Yeah.
You do. Okay. So that means you've got quite a lot of embeddings. We'll talk about that later, but it means you need an embedding for each of the 30.
No.
Oh, no, because they're the same task. Oh, yeah, true. They're not augmented. Yeah, okay. So, yeah, I mean, the detail of what you described really matters, and it reminds me a lot of ReArc, the ReArc repo. They didn't quite use the tricks that Ivan used, but just to recap and use your example, you have a seed set of data. One of the seed tasks might be joining 2 dots with a line, as you mentioned. One of the seed tasks might be rotating. I'm giving simple examples here. So you might have one seed task joining a line and one rotating, and you have a description of each of those in English. Now, the descriptions are augmented into multi-part key value pairs. But taking those descriptions, you ask the LLM to combine those into a more complicated problem. So the LLM will then provide a description in human language for some problem that rotates and requires joining 2 points. And once you have that description in language, you now move to that pipeline you described where you have 2 steps, one to generate code to generate the input, which sounds a bit meta, but that is a key idea because it means you can generate multiple input examples for the same description. And the nuance there, which you mentioned as well, is Ivan wrote unit tests to test the code generation for the input grid. And that's how you verify the quality of input grids. And then the last thing, and you can correct me here if I'm missing things, when you generate the transformation, so the function that goes from input to output, the way you verify that correctness is by running it on all of the 30 input grids and checking if you get the same output. So there are two verification ideas that Ivan came up with there that allow you to robustly generate samples that are good. Is that a good summary?
Yeah.
And so essentially you're mixing concepts, basic concepts from tasks to get more complex concepts. And what you found is it's important that the basic concepts include ARC AGI II difficulty concepts. If they only include ARC AGI I difficulty, i.e. the HARC or BARC, then you find performance is not good enough downstream. So it's important to include the ARC AGI II difficulty primitives. Is that fair?
Yeah.
Now, by doing this, you're compounding basic tasks. So you're now allowing for training the model on kind of a quadratic space. Would you agree with that? Because instead of just training it on linear, it's
quadratic space because it's we're not covering all the combinations.
Right.
And there is a lot of drop. So we started from 260K combined descriptions.
Right.
But by filtering those where the LLM cannot find a good input code, and those where the LLM could not find a good input to output code, this dropped to a bit more than 100. So more than the acceptance rate, especially for the one involving ARC AGI II was 50% on me.
Yeah, understandable. So you dropped a lot there.
Yeah.
Now, I don't know if you looked, but do you think if you checked the private, and you can't do this, but if you check the private tasks to see which ones you got correct, do you think those tasks would be close to the compounded tasks in your synthetic data set?
So that's a debate. Some people told me, oh, you just replicated the hidden test set. I don't believe at all this is the case. And when I said this to our price people, they doubt it as well. So it's just that there's some, by training the model, and the decoding is important as well, but our pipeline has seen enough puzzles to kind of learn how to learn. That's my take. So the model is pre-trained to learn from few examples. Really, in a specific domain, it does not. If you apply it to something else than ARC AGI, it's not relevant. But so I don't think it's rote learning, memorization. It's more kind of so it's called transduction. So understand enough of the puzzle to be able to compute the output. I really believe this. A transformer is really a good tool to learn functions. So we fine-tune the transformer so that it could adapt its learn function quickly with few examples. I really believe that's what we do, and it's not memorization of the puzzle he has seen. Because we tested with, we don't use the evaluation data set in the training data, in the pre-training data, and we evaluate on the evaluation data set. So these are different tasks, and it was performing like 30%. And when we submitted, our score was close. No, I don't. But some people are convinced we just by chance, or I don't know, we generated enough puzzles that we covered the test set. I doubt it. But only our price people would know. Huh?
Right. Yeah. I mean, let me describe my mental model, and you can comment on it. So the way this is a two-phase approach. We haven't talked about the second phase yet. We haven't even talked about training. We've just talked about data, but you pre-train, and during pre-train, my mental model is you create a landscape that is familiar with these compounded problems, these compounded tasks. So you've got a rough landscape of now not just single concepts, but combined concepts, because your data set has got combined ideas. And now you bring this landscape into the competition, and now you do gradient descent. So you start to search on this landscape based on the problems you're given at competition time, which are hidden. And because you have the compound coverage, you're able to navigate that landscape. And in, 24% of the cases, you're able to come to a solution. Thoughts on that?
Yeah, it's correct. Yeah.
Do you think that's how it works? So what happens then if there's a concept that is in the competition that is not in the seed data? Is that why you get 76% of them wrong?
I don't know. So we have not done. So one thing is what we did describe. Just a lot of it happened in the last 2 weeks of the competition.
Yeah, right.
And that's also why we did not overfit. We did not have time to overfit.
Yeah, nice.
So we've not done a post-hoc analysis of which puzzles are solved by our solution, which aren't. For instance, honestly, it's embarrassing to admit it, but in our prize, there are two categories. There are puzzles where the output grid is the same size as the input grid.
Right.
So AGI I, it was 2/3 of the puzzles. I did not for ARC II. Maybe our solution only works when our output size is the same as input size. I don't know, but that could be a limit we have. And so there could be a limit like this, or there maybe it cannot find puzzles where objects move around, but it finds puzzles where the input is duplicated and processed. Or there are different concepts, as you say, and maybe some are totally unlearnable by our approach. That's possible. So that's what Ivan's hypothesis was. Our solution captures some of the concepts and do well on these and fails on the others.
Right.
Honestly, we that's something we should do. Maybe I will do it.
Nice.
But no, so I can't answer. So
yeah, I know it's a speculative question.
Yeah. But if we had more time, I would have done it, because then, say, if we don't solve well in problems where output size is different from input, then we just train on those where the size is the same, and that's it. And I'm sure it would improve overall.
Right.
See, so I don't know.
Yes, it's hard to know. Another speculative question I have is, I believe ARC Prize have said publicly that one of the reasons ARC AGI II is more difficult than ARC AGI I is because they intentionally combine concepts within ARC AGI II, whereas in ARC AGI I, the puzzles are often more limited to one concept. And so my question is, if your pre-training data is somewhat quadratic in concepts, if there was an ARC AGI IV where they had 7 concepts, would that space just be too large then?
No,
be able to.
So again, we are not training on the quadratic space. We are training on the sampling of the quadratic space.
True. Yeah.
No. If it's 1%, 1 out of a billion, honestly, I don't know. So,
yeah.
Let's say we started from 3,000 elementary descriptions. So I should take the square. It would be 9 million.
Right.
We use 260K only, so it's a fraction. And even if you combine 2, there could be different ways to combine. So no, we have a small fraction.
It's a big sample. Yeah, it's a small sample.
Maybe we create a task that looks similar to some of the test tasks, but not all of them by any means. That's for sure.
Yeah. I mean, I can certainly see why they wouldn't have to be exactly the same, because you would expect there'd be some kind of transfer, but it's hard to answer how much transfer.
Some generalization happening, because the crux of the solution is to learn from the examples in each puzzle.
Right.
So you can have new puzzle and solve them even if you never saw them, provided you have a system that can actually learn from few samples. That's what ARC AGI is about.
That's what it's about.
Factor.
Yeah. Now, the private models like GPT 5.1 and Claude 4.5, their performance has improved a lot recently. Do you think it's possible the reason they have improved is because they have done exactly what you have done, which is compounding, combining some of their raw data.
Is zero doubt in my mind that something similar. There is a difference, though.
Wait, when you say zero doubt, you think they did or they didn't?
They did. There is a big difference. They use code generation and code execution in the solution. That's why their cost per task at inference is 10 times or more than us, because they use code execution. So the process we did to generate likely Python code for the transformation, blah, blah, that we did for generating pre-training data, they do it at inference. So they pre-train their model with tool coding, that's for sure. And these frontier models, they know what ARC price is about. You don't have to say, oh, it's a grid with this, and you have to...
Right.
And it just give them the JSON, the input, the output, and they know about it. So,
right.
Of course. And this is true for every major benchmark. They take all benchmarks, they see how they can generate training data for it and put all together. And given it's a large mixture of experts, it's as if there is an ARC AGI expert inside of these frontier models and MMLU expert and for each benchmark. So they do have a good ARC AGI expert inside the mixture of experts.
Right.
That's
right.
So yeah, you cannot do well on using LLMs. The way to do well with LLM is to train it on relevant data. There is nothing, and that's the point of surely why he wanted to build ARC AGI. He says LLMs they are good on things similar to their training data, and I agree. So I designed where we kind of defeated the purpose is we use the LLM to generate training data so that the LLM can do reasonably well. So, but and all the frontier model they run on synthetic data, either created upfront or generated on the fly with reinforcement learning. But of course, they try
using similar principles
similar to each benchmark.
Yeah.
Why they would not do well?
So if I wanted to be very annoying and make some tasks that I thought would be very difficult for you to solve in Kaggle, my proposal would be I would start off with primitives, some simple tasks, and I would just test them out on Gemini 3 and on Claude 4.5 and see if they have any understanding whatsoever of my primitive concepts. And if they had no understanding, I would select those primitives and I would try and compound these primitives that I empirically have somehow tested they are unfamiliar with, because that would then make it very hard for you to generate any descriptions to train on other than human labeling like you did.
Well, that's what they did. If you look at ARC AGI II, when it was started, the performance of frontier model was less than 2%.
Right.
That's what they did.
So it's by definition, that's why that's low.
That's they said it in the ARC AGI II paper. The best one, like Claude Sonnet 4 was 1.3%. I'm looking at the board. GPT-5 1.9%.
Yeah.
Sure. Yeah, they did exactly what you say. They checked that the tasks were difficult for frontier LLMs.
Right.
Sorted.
Right. And how is it then that the models get to those concepts? Do they just blend in concepts that are not ARC related? For example, as
I said, they generated synthetic ARC data and trained the model on it.
Right. But what's the seed? They got to have some seed to spur the concept.
They did something similar to what we did. I don't know, but Google, for instance, they shared an ARC AGI I problem generator. They have a data set with a generator.
Right.
For ARC AGI I, but of course they did the same for ARC AGI II.
Yeah.
No, it's how you improve LLMs by creating relevant training data.
So moving to architecture from data preparation, does the architecture matter at all? Or do you think your data set could perform well with many approaches, diffusion, mass diffusion, TRM, architects? Is there really any benefit to any of them?
So we know for sure that training with our data improved Qwen models and TRM models. So I'm pretty sure, for instance, if the second place, the architect trained their diffusion model on our data, they would improve their score, definitely. I bet on this.
So is there anything that matters about architecture?
I'm not saying the architecture does not matter. I'm saying, and we've seen it, the more data, that's why we improve quickly at the end, because data was being generated. And the last batch of generated data came in like a week before the end of the competition. And then we pre-trained models on it. And when they were ready, that's what gave us the highest score.
Do you think you could filter that data down a lot by using cosine similarity or by measuring difficulty?
No, I believe the opposite. We should, if we had 1 more month, we would have generated more data. We would have got an even better score.
So that jump up the curve at the end was closely aligned with data quantity.
And larger models.
Right.
For large parts, so we use TRM. I work on TRM and Ivan on Qwen models. They use Qwen to be VL, so it's a visual language, a VLM. Thinking that given it's also a VLM, it would grasp the puzzle better.
Right.
But in the end, I asked, but can't we train larger models? So he tried Qwen 4B. And the training of Qwen 4B ended the day before last. I'm not kidding.
Okay.
So the last day we had a choice of Qwen 4B alone or Qwen 4B with TRM. We had both. We said, okay, let's be sure submit Qwen 4B alone because we were not sure the ensemble would run within the 12 hours. So that's what got the best score of the competition. Qwen 4B alone. In mid submission, using TRM improves a bit, so we had better score. But,
right.
But the priority was to generate as much data as we.
I was surprised you thought ensembling might help because the data set is the same. So it strikes me that you might get pretty similar tasks solved. And I know you reported you found 3 tasks.
No. Ensembling always worked because even if you train on the same data, different model architecture don't learn the same. So ensembling is always a good option to improve quality of prediction, always.
Because you think the architecture has got different capabilities?
It's not a thing. It's what I've observed in more than, I don't know how many competitions I've done, but in dozens and dozens of competitions. And everybody, you ask every Kaggle grandmaster, they will tell you the same. Ensembling is always useful. It's extremely rare that ensembling is not useful. Extremely rare.
Go ahead. Sorry.
It with few metrics, work cases, but nano ensembling always help. Maybe not much, but it helps.
And if you're looking at TRM now, one of the design choices with TRM is to have an embedding for each task, including for augmented variants of that task, which means you need an insane number of embeddings. So
I won't name them because that's what I did in the previous year. So previous year, I implemented a 2D transformer. So there are two ways. Remember, a puzzle comes with several input-output pairs as training example, and then you have one or more test pairs where you only have the input and you have to do trade-off. So you have models that take all the pairs of a puzzle and then use that to infer the transformation. So that's the architect solution. And that we improved with Qwen and few other tricks. So that's one. And then there is another view where you just give one input and you train your model to compute the output. But then, of course, you need to tell the model which puzzle it is about to solve. Because from a given input, the output depends on the puzzle. So this dependency is captured via the puzzle ID and in transformers, the canonical way is to map an ID to an embedding. So I did this last year. So that's not an innovation of TRM.
Yeah, sorry, fair point.
Innovation, no, but I mean, it's, I did not publish in a conference, did not make a lot of noise. Maybe I should, but I'm not sure this was, I'm not sure I was the only one doing it. Having an embedding proposal is key in the, I believe in TRM applicability. Because you learn what is specific to a puzzle and then you learn, you have a system that learns quickly if it even. Basically, the puzzle embedding acts as a context, like a context for LLMs.
Yeah, it encodes the task, the task-specific information. But what it means is you had to reduce your data set down to about 3,000 tasks.
Exactly.
So how did you pick those? Because you had about 100,000.
So I've generated a data set in several batches, a dozen. When I say batch, it's not like a training batch, but generating few thousand or more sample that puzzle at a time. So he had like a dozen of files with thousands of puzzles. I basically took 1 out of 20, the first 1 out of 20 bit of each batch.
I see. So somewhat random then.
Oh yeah, random. Well, I took the first it generated, but it's like random. I ignored some, so I asked him which one I should use. He said, "Oh, you can ignore some of these because in his experience for Qwen they were not helping a lot." So basically, he said ignore those few batches and kill these ones. And then I played. I could run with 1 out of 20. I tried 1 out of 10, but it was slower. Of course, more data. So I had to make a choice. But yeah, I should probably see what happens. I tried first with more samples, and then I had good errors. So I don't know. I did not have time to investigate. But there is some there are some issues if you use too many embeddings. So I don't know if it was memory errors or not, but there are issues with more. So I stayed with the same number of puzzles after augmentation. So you mentioned augmentation. That's something important.
Yeah. How did you do that?
Everywhere. So there are two families of augmentations. So augmentation means given a puzzle, you generate automatically a new puzzle. So one family of augmentation is geometric. Given you have squared grids, if you rotate them or flip them, you obtain a new grid of same size. So if you say you flip all inputs and all outputs left, right, you have a new puzzle, which is similar to the previous one, but not the same. The other augmentation is to permute colors. So you swap yellow and black or whatever. So if you have 10 different colors, you have factorial n color permutation times 8 geometric transforms. So you can generate a large number of puzzles from a given puzzle. So depending on the source of the data, so which batch, and a different number of augmentations were used for Qwen. So let me see if I see it. Yeah. So tranches, for the data set that existed before, like real or competition data, he used 256 augmentations. And for the synthetic data that was generated, he used 24 or 32, depending on the batch.
And that's for the architect's architecture?
That's for Qwen. So the architect, so let me be clear. The architect solution, we took the decoding part. They use a different model. They use the Lama-Nimotron, which was an 8B model last year.
Right.
So use a different model.
Okay.
So that's not, that's pre-training. So this is, we put it inside the architect section, but it's independent. We just train Qwen, given the training pairs, and one input produce the output. So that's how it was pre-trained. So this has nothing to do with the architect.
Right.
Where the architect idea was to use simple tokens. So they implemented their own tokenizer. We kept Qwen tokenizer, but with just simple representation, token 0 to 9 for the colors.
Yep.
And then one token for the new line, one token for start of input, one token for start of output, and then few tokens needed for Qwen formatting, like LM start, LM on, and padding. So we had 16 tokens only, but we kept a Qwen tokenizer. And then also patch the embedding table in Qwen to just 16 relevant tokens.
Okay. Yeah. Okay. Thanks for going through that. And just to be clear, when you train the Qwen model, you input all of the examples, all of the example pairs?
All the training example pair for puzzle, yes.
And does that mean 30?
Yeah.
So that's a really long context length.
Yeah. Well, that's for training you can afford.
Right. Of course, at test time, you have a maximum of, I think, 10 in the competition, right? Something like between 2 and 10. Yeah, cool. So just briefly on the TRM, which is a recursive model, I suppose the aura tells you what I'm going to say.
That people say recursive, but to me it's iterative.
Iterative.
You have a loop. Yeah, it says recursive because so TRM is a transformer. So people believe, it's a new architecture. No, it's a transformer. It's a new way of using a transformer, but TRM is a one block transformer. So 2 blocks. You have, in a transformer, you have the first layer, which is embedding. So you have your tokens that are mapped into your latent space. So here it's 512 floats per token. And then you have a block in a transformer block. A block is an attention layer followed by a feed forward.
Right.
Yeah. And this is repeated. So in GPT-2, there were 12 layers in NVARC also, I believe. And we don't know in the last frontier models, but it could be it's dozens, if not hundreds. I don't know. So theorem, it's one block only. So instead of having 12 layers, it will loop 12 times.
Yeah, right.
Around the same block. So that's a no, but it's looping. So they say recursive because the output of the block is fed in. You call again the model on the output of the model. But to me, it's iteration anyway. People say, if okay, fine.
Cool. If you iterate, obviously you can save parameters, which saves you VRAM.
Yeah, and I use a single block transformer in a competition a few years ago.
Yeah.
It worked fine.
Okay.
And as you say, you have less parameters, so it's faster to train. But I tried with others and it was not the best, so I did not thought it was that important. But
so would
a few years ago,
yeah,
sure, other people have used single block iteration before. I don't believe that's the novelty of theorem. The novelty of theorem, if you ask me, is
I ask you.
You have first, the input and the output must be in the same space.
Yeah.
So here, the input is a 30 by 30 grid, the output as well. So the great idea of theorem, and it's hard to say which is a theorem ID, which is a HRM ID.
Right.
The two, or theorem is a distillation of HRM in a way, simplification. But it starts with the input, a random output, and it loops. And during the loops, the output is refined into what it should be. And it's more effective. A third, called a latent value, is added. So you start with input plus random output plus random latent. And through iterations, both the latent and the output are refined. And at the end, your output. So it's a bit mind-boggling that it works by mixing input and output and then extracting output at the end works. But it does to some extent. So that's really a novelty. So again, the novelty is to loop over a single transformer block and to have output refined along the way, like in a diffusion model, if you wish. Similar.
Do you think the big labs are doing that?
Sorry? No.
Do you think the big labs are doing that? Do you think they should?
They have, for instance, Google published a paper about nested learning recently. So the idea of moving away from autoregression, where you generate tokens one by one, and taking a generated text and revisiting it is appearing. So theorem does it at the core, but if you look at the architect solution this year, they do it as well. So they iterate through a diffusion model. So I wouldn't be, and we see, as I said, now a few Google papers on new architectures, but this is one thing, to have a progressive refinement of the output. So there is definitely something being explored. I don't know. Then is it used in current frontier models? I have no clue. I don't know. I have no.
So I'm coming to the last few questions here. Third last question. You talked, I think I saw in your interview with ARC Prize.org, you mentioned RL, and it's obviously challenging because you don't have enough compute right now to do long reasoning traces. But do you see the future being in RL? And there's a criticism that RL helps to make outputs more reliable, but not really reach solutions. For example, the pass at 1 might improve, but pass at 1000 doesn't really improve. So Does RL make sense? Is the reward too sparse? How do you densify the reward?
So I did not do pass at 1000 for theorem, but I measure pass at 128 because that's the number of augmentation I use. So I train theorem longer, so with more epochs than during competition. During competition, I got a score of 10 with theorem. And then I trained it more, and I got a pass at 2 out of 18.18%.
Right.
Quite good.
Pretty good.
But the pass at 128 was almost 30%. So if reinforcement learning moves TRM to 30%, that would be similar to our solution score. That would be significant. So yes, RL may just be good at reordering the generations, but that's fine.
That's useful.
Yeah, that's useful. I have no clue if reinforcement learning would work well on ARC AGI II. I have a gut feeling that for ARC AGI III, it would help.
Okay, cool.
It's a gut feeling. I have not.
Haven't tested.
No.
Yeah. Second last question. You've heard of dreamcoder, I assume, the dreamcoder approach. Do you think that has potential?
I honestly, I don't know. Reading that paper is on my to-do list. So I've seen people tried dreamcoder at the start of ARC AGI II. The one problem of ARC AGI that there are cool new so fancy papers. Let's say fancy. So new architectures, new ideas. But if you look, they solve less than 10% of the tasks. So it's not clear, including TRM. TRM was run by ARC Prize on 3 H100 nodes, so 24 H100 for one day. It's significant.
Yeah. Right.
And it scored 6.8%.
Right.
That I got 16% in a couple of hours. It is a significant leap, and it comes from the training data and pre-training, then using TTT. So you need quite a lot of scaffolding, but it's still only 16%. It's not. So
Right.
like there is a new recent paper using a visual transformer, and they say, ARC AGI is a visual task.
Yes, VARC, yeah.
Yeah, and they get 8% on ARC AGI.
Yeah, right. Same as TRM with no recursion.
It's not really a proof that they solve ARC AGI II, right?
No. But maybe you don't need recursion.
No, but
or iteration.
My point is, and dreamcoder, people who tried it, they solve few percent. So it's...
yeah.
My point is, so we did not use new models. We reuse other models, Qwen or Theron.
Right.
And it shows that too, but we have a much, much better score. So some people dismiss our solution as being not new, and I disagree. The fact that we beat by a large margin everyone else. And remember, when we got our score on ARC AGI II, there was only one better score at 30.4%.
Right.
But at the cost 150 times more expensive than us.
Right.
That's all. All the now Gemini 3 and Grok and Claude have better score than 30. But all this came after the competition end. So
I know. And you couldn't talk about it for a month, which
and I've been frustrated because we really were on top of the leaderboard for. But my point is, if we could get to that with small models, it's because we did something new, and there's something new on the data generation.
On the data side.
And people underestimate the importance of training data.
Right.
So if there is one lesson from our solution is better training data.
Better training data.
Everything else.
Yeah. Last question, Jean-François. What are your recommendations for the ARC prize organizers? Maybe one suggestion of something that would make it easier for great research to be done.
Well, so I said it on Twitter as well, Alex, to allow larger GPUs. So the AI Math Olympiad that started a few weeks ago on Kaggle use H100. And with this, you can run reasoning models. So if they want, maybe they were disappointed to see us winning with no reasoning and no code generation at inference. And the reason is the limits we had on Kaggle. Cannot afford a reasoning model with that number of tasks with the GPU that was there. So if we have larger GPU and maybe more time for inference, then there is more room for innovation on the architecture side.
Okay, great. That's clear. That's clear.
So it's not that my point was not to prove that you can do well on ARC AGI without code generation and without reasoning. That was not the goal. It's the way we found to do well.
Right.
Because of the constraints. We had to move reasoning and code generation offline. But I'd love to, for instance, there's this poetic solution, which is an agentic loop on top of Gemini. I'd love to have a solution like that on Kaggle, but we need more compute to run this.
And that's why you're a grandmaster.
Maybe.
Merci beaucoup, Jean-François.
Merci. J'espère que j'ai répondu à toutes les questions.
J'ai très bien apprécié. À bientôt, j'espère.
Merci.
Au revoir.
Au revoir.